Freddy Bouchet, who is a research director at the CNRS and the Ecole Normale Supérieure in Paris. So Freddy, probably most people know him already, but he's a physicist who's been working in statistical physics and climate science. And he's going to talk about extreme events and different aspects of the analysis of extreme events in the climate system. I also want to highlight that Freddy has received this year a Callier Prize from Cyan for mathematics of planet Earth. So,
Grazie mille, Francesco. Thanks a lot. So thanks all of you for coming. So I will discuss the recent approaches we had using mathematics and statistical physics in order to improve the way we study climate extreme. There is a theoretical part. It will be mainly useful through computing. So we develop algorithm, and so I will show you some application. So as you probably know, I was trained as a theoretical physicist. So most of my work so far was in theoretical physics. So I will show you just a few examples of some recent work in theoretical physics. But these talks will be mainly concerned with application, climate application. Okay, so let me go on. So you can see a few of my colleagues. The other ones will show up during the talk. So those are the most recent publication. So I want to begin by an introduction to explain why do extremely rare events matter? Why do we care to compute events that are so rare? So of course it is because of their impact. So I will try to illustrate this in the case of climate dynamics. Then we have several approaches. So the second part will be concerned with what we call emulators, which are a way to learn effective dynamics and accelerate the dynamics. The third part will be about rare event simulation, which is a way to oversample the dynamics of extreme events, of rare events at a reasonable cost. So the fourth part will couple the two previous ones. I will discuss a few applications, and here I will discuss a bit about tipping point, but we don't have recent results about tipping point. It will be more like older result or perspective. Okay, so as far as theory is concerned and mathematics is concerned, my work was using mainly large deviation theory. And so, for instance, long ago, during my PhD, I work on the statistical mechanics for explaining the self-organization of geophysical flow. So this was an example of equilibrium statistical mechanics. So this was back in 2000, and so this is the report, but my PhD thesis was back in 2001. And so we were already using large deviation theory. And so we were proving that if you want to explain the self-organization of vortices or jet, for instance, this is the great red spot of Jupiter, then you can look at the numbers of ways you can mix values of vorticity or potential vorticity. So for people in statistical mechanics, this is just like a Potts model with long-range interaction. And so we have explained that, and so we have also derived fully the statistical mechanics for it. And then we show that the probability to see something, so this is, for instance, the field that describes the potential vorticity, is proportional to exponential of minus s, where s is an entropy functional. And so then we can explain that the structure emerges as the most probable state, but maximize the entropy. And so this explains the shape, the stability, and all the physical property of the spot. So here, so for instance, this was in my PhD, where we have shown that we can recover all the properties of a great red spot. So this was, for me, the first time I learned about large deviation theory and the connection between large deviation theory and dynamics. So later on, because the real world, especially in climate, is not at equilibrium, this previous example on Jupiter is very specific because we have a huge timescale separation, and then it is close to equilibrium. Because we are far from equilibrium for climate, I mean, we had to go to large deviation theory in order to study directly the dynamics. And so for this, we follow things that were done in statistical mechanics by many colleagues. And so I decided to focus specifically on large deviation theory for rare event. And so you see a few examples here. So for instance, this one describe, so you have 3 values which describe the structure of zonal jet for Jupiter troposphere. And so there are 2 attractors, one here with 2 jets, one there with 3 jets, and this is the concentration of all the dynamical path to go from one state to another. And so this is what we call an instanton. And so this was the first description of instanton related to climate dynamics. So we have made a series of work with Eric Simonet. This one is also with Joran Roland. And so we have tried to apply this to problems more related to the Earth. But for the Earth itself, we have not gone so far. But we have made several works where we try to show that there is actually tipping point and bistability in Earth-related problems. So I will discuss very briefly a current work with Juan Zhang, a postdoc. Currently, we try to study the tipping point of the subpolar gyre and its relation to the Hammock tipping point. So more recently, I have been interested in large deviation theory related to kinetic theory. So probably you know what are kinetic theory. For instance, we want to derive the Boltzmann equation from the Newton equation for interacting particle for a dilute gas. But so this is the typical example of kinetic theory. But there are many other examples of kinetic theory, and this is another one. This is the classical theory for explaining the evolution of a wave packet in a wave turbulence. And so the theory itself dates from the 20s in physics for solid condensed matter physics, but it was used by Sakharov, for instance, in wave dynamics for other problems since the 60s, and it has been used a lot since the 70s. For instance, Hasselmann, that got the Nobel Prize, has made a lot in order to use this for climate sciences. So here we decide, so this kinetic theory, what they do is they describe the most probable evolution of a coarse grain, a mesoscopic vision of the particle system. And so for instance, for the Boltzmann equation, you have the distribution of particle in velocity and position space. Usually it's denoted by F. And so the Boltzmann equation describes the most probable evolution for it. So what we have tried to understand is the evolution of all possible evolution. So in order to get the fluctuation, typical fluctuation and rare fluctuation. So we have done that for a series of kinetic theories. And so here you see it for the wave turbulence case. I just show you the result. Here the field N here describe the Wigner transform, which is a local energy spectrum for the wave field. And so this notation means the probability to have the actual one here, n tilde, n hat, be equal to something, n, starting from n naught. So this is the probability for a path during a duration tau f, between 0 and 2f. And then we can prove that there is a large deviation principle, or you can show that there is an action. So an action meaning that it is the integral over time of a Lagrangian that depends on n and the derivative of n. And so L, the Lagrangian, is the Lagrange transform of H, and this is the formula for H. So the result here is to compute H from first principle. And so we have done that here in that case. first with Jules Guyot and Gregory Eying for the homogeneous case, and then there are several generalizations and use with, so Jules was a postdoc with me at that time. Yohei Onuki is a colleague in Japan. And so Brice Douai is a PhD student but just ended his PhD a few weeks ago. So this is an example where we derive path large deviation theory for the kinetic theory of wave turbulence. So I am very fast, so it's normal that you miss it. I didn't explain it. So in this case, it's a scale separation between if you look at the spectrum, it has a typical scale, and then you will look at the evolution of the spectrum on a scale which is much larger. Okay. And then you have another small parameter, which is the nonlinearity. So you have to scale these two parameters together such that the relative contribution of both things are of the same order. So it's impossible that you would have understood. I want to tell you this kinds of work and result. And so we did that. We made several similar works for the Boltzmann equation. Actually, the Boltzmann equation, the result was somehow known before, but we explained why it should be generic. Actually, Yu Deng, that got the Field Medal a few weeks ago, got the Field Medal partly for proving these things mathematically, both for the Boltzmann case and for the wave turbulence case. So we also, with my PhD student Wassim Feliachi, we also did that for all the other classical kinetic theory, plasma beyond the Debye length, systems with long-range interaction, and the weak turbulence theory, as I just said. Okay, so but now I want to, so 10 years ago, I decided to have to go beyond these academic problems and to have more impact on real things, especially related to climate, impactful climate event. And so here the point would be to try to use this basic concept and idea, but to be relevant for real world problem. So I just first want to convey the idea that very rare events do matter. So here you see a graph where you see the last 25 years. And so you see the numbers of annual deaths by major climate-related disaster. So basically you see that there are 3 points that correspond to 3 events. The Western European heat waves in 2003, a cyclone in Myanmar in 2008, and the Russian heat wave in 2010. So the order of magnitude is 100,000 to 150,000 people dying. And all these 3 events were unprecedented. We have not seen them before. And they are all different. So basically it means that from the point of view of observation, those 3 events do not belong even to the tail. We have never seen them before, right? So this was, so this is what we need to study. And so this is a severe challenge for science because we have a lack of data issue. We don't have any data, unprecedented event. And so we will have to use models, try to connect this model with the reality. But even if you use the model, those events are so rare that you will have a great difficulty to simulate them. And so this is where we will try to give some new tools to study those events. Another example, hopefully this will never happen, but this is the impact of heat waves in South and Southeast Asia. Here, what the color you see corresponds to the wet bulb temperature. The wet bulb temperature is something that takes into account temperature and humidity because it is important for the people that are that are confronted to this heat, whether they can transpirate or not, and whether this transpiration will be efficient or not. So when you have a red color, it is the last percentile, meaning that 1 day over 100 you have this value. It means that 3 days each year you would have wet bulb temperature of the order of 31 to 32 degrees here where it is red on average. So those temperatures are considered to be the threshold beyond which a human being cannot stay outside more than 20 minutes, let's say. Okay, so basically it becomes somehow inhabitable without a very strong change of the way our society is organized. So 3 days a year means that it can be the case during 1 month, during a specific year, for instance, right? So hopefully this will never happen because this is with a scenario RCP 8.5, and hopefully we will never see this scenario. Well, this will depend much on the political process, but we have all the tools to avoid it, let's say. Okay, so this is another example of a severe event that really matter. So as I already said, there are 3 key problems. The historical records are way too short. The climate models are wonderful, but they have biases. And the more precise they are, the more computationally costly they are. And because of that, the most extreme event cannot be computed using direct numerical simulation. And so I can summarize this by saying that the main scientific bottleneck is a lack of data issue. So back in 2015, so I was trying to look at a rare event in climate, and I recognized that there was a huge scientific gap. And so that would require entirely new mathematics and computational approaches. And so I also recognized that it would demand a long and difficult research effort. And so we started with trying to show that rare event simulation would be useful. And so then we started with Eric Simonet and Johan Roland. And so this was the first application of rare event simulation to systems with a huge numbers of degrees of freedom. In that case, it was a stochastic PDE. And then with Jeroen, we studied rare event simulation for deterministic chaotic system, showing that they work even if initially they were thought of being useful for stochastic processes. So then we have developed that. I will show you some development of these things. So now we have 3 different approaches. So this one, rare event simulation, I will present. We have also dynamical emulators. So dynamical emulators are, it is an AI-based approach. So with AI, you learn the transfer operator in the transfer operator not for the space of function, but for in the physical space directly. And based on observed data or based on climate model output, and then this will learn an effective dynamics. And the key point is that this effective dynamics will run 1,000 to 10,000 times faster than the initial climate model. And so then, if it works, it means that we can have much more of this rare event that matter. So the second approach, which is the oldest one from the point of view of my own research, is a rare event simulation. And the third approach, which we are not developed ourselves, but we now use because it is complementary to the 2 others, is the Bayesian general extreme value theory. And so this is a way to connect to the real world observation. So this explains the plan of my talk. So I will begin by the emulator, I think. Okay, so this is the point. Here we want to learn an effective dynamics which run fast. Okay, so everything comes from a series of work So in the academics, a few people were trying to build such emulator for now 10 years, but there has been a huge change in 2022 with a set of papers. So you see from NVIDIA, Huawei, and DeepMind. And so the big tech company, they have decided to build such emulator in order to do weather forecast. So you see the skill of this emulator here. So this is a plot from ECMWF, the European Center for Medium Weather Forecast, Medium Range Weather Forecast. So you probably know that it is based here in the UK and in Italy and in other parts of European countries. It is the European one. It is the best worldwide model for weather forecast. And it is based on physics. It basically solves the PDE for the fluid mechanics and the Schwarzschild equation for the radiative transfer. Okay, so you see the skill. So this is, for instance, for the 2-meter temperature root mean square error as a function of the forecast day. So you see, for instance, the red one, which is the physical model. So you see that you have error. This is in Kelvin for the root mean square. And so you see that after 10 days, you have an error which is of the order of the variance of the standard deviation. So then you have lost the predictability. So the red is the physical model. And so now you see the GraphCast one, this one, the orange one, is the one by DeepMind. And you see that it is actually performing better, statistically significantly better than the physical model. So they were able to do better than the physical model for the weather forecast. But you see that the improvement is marginal. It's only a few percent, basically. So it's a big deal because it's a completely different approach. But from the point of view of application, it is not such a big deal. The main point, from the point of view of application, is that this AI-based model runs much faster than the physical model. And so what ECMWF did then is to see these things happening. So they decided to restructure many things. And now they have a new AIFS. IFS is the name of the physical model. AIFS is the name of the ECMWF AI-based model. And now they are able to do better than Google. Okay, so how does it work? So this is the technology we will use ourselves. So here I have written climate model, but this slide is valid both for weather and climate model. So you take all the fields you need, pressure, temperature, humidity, everything in the atmosphere. And so you know you have series data sets, you know them. So you look at T and T plus delta T, and so you will learn the transition, the probability to go from one set of field to another set of field. And so this will be learned by a neural network. This neural network can be deterministic or probabilistic. And so this is called here T theta. Theta are the parameter of the neural network. And then once you learn it, you roll it up so that you are able to reproduce autoregressively the trajectory. So basically, you have learned an effective dynamical model for this. So ourselves, we use two architectures that were developed for the weather, SFNO and the Pangu weather. And so we have tuned them such that by contrast with the emulator for the weather, this emulator will be stable for a very, very long time. And so then we have tuned them such that they are valid not just for making forecast, short-term prediction, but also such that the statistics of the invariant measure will be more or less correct. Okay, so then we have emulators, so they run actually 1,000 to 10,000 times faster than the physical climate model. And as I said, they are stable.
So, I mean, that seems to have a strongly Markovian assumption living in.
Yes.
Seems to me incredible.
No.
You can't do that by having the emulator know about the time series to date, not just the previous time series.
So the physical model is Markovian. So it has a time scale when you compute things, a time scale of, I don't know, a few minutes maybe, 10 minutes? Depends, for weather forecast, maybe a few minutes, right? This is Markovian. The delta T here, which is used for the emulator, is 6 hours. So on a 6-hour time scale, it is more or less Markovian. And actually, the emulator which is used is using the field at 6 hours before and 6 hours before. So it uses a set of a few, an embedding of a few, showing that it is not exactly Markovian.
When you have a system which is Markovian and you do any kind of dimensional reduction to it, it isn't Markovian anymore. And so I would imagine the emulator was building, if it's fast, was building a lower dimensional model than the one it's trying to emulate, which won't be Markovian.
Yeah, this is a very important question, and we don't know the answer to this question. So basically, it is faster because he is doing another kinds of computation. So whether he has learned something which has a lower dimension or not is not clear yet. The numbers of parameters which is encoded is huge. And so, I mean, this is a question we actually discussed with several people here during the last few days, how to get information from the simulator to see if there is an effective dynamics that we could interpret or not. So this we don't know yet. Yes?
Something I can understand is that what with the simulate, with the not the emulator, so with the model, how you were doing because now you show that you have different data, and then you have the emulator that essentially tries to find the mapping. So before, how you are doing it with the physical model that you have with precision.
So there are two fields of application. The weather, so it is the physical model which is used to produce the weather. So they produce a data set which is called ERA5. And so they have trained the emulator using the ERA5 data set. Right? So our application is slightly different. We use a model here. This one is PLASIM model. So this is what is called ground truth. It is our physics. It is our climate model based on the law of physics. So you see it running. What is represented is the geopotential height at 500 hectopascal, which is just like pressure field in the middle of the troposphere. And so you see what the physical model does, and here you see what the emulator does. So they are not, you should not compare directly, it's not the same trajectory, but what will be compared are the statistics of the two. Right? So here you can just see that qualitatively, at a qualitative level, it's the same thing. And then I will show you quantitatively that it is actually the same thing. So here our emulator has been trained on the output of the model. And so here we have tested how good it is. So for instance, we computed what we call the climatology, which is the average. So here you see the average 2-meter temperature. And so here you see the error with our two emulators. So this is the physical model. So this is the error for the SFNO architecture, and this is the error for the Pangu architecture. And so you see that we have biases of the order of plus or minus 0.5 Kelvin, where it is the worst, let's say. And so we have biases which exist, which are not well characterized yet. We don't know if these biases are led to learning or something else, but they are rather small. So those are for averages, but we have also computed the main mode of variability using EUF. So this is the main mode for the northern hemisphere, which is called the northern annular mode. And so you see the pattern for the physical model. So you see the pattern for the SFNO plasm and the pattern for Pangu plasm. And so you see that the emulator reproduces very well the modes of variability. And so this is the spatial pattern, but you see also here the autocorrelation function, where you see that the temporal aspect is also correct. Okay, so we have a tool that runs thousands of times faster. Can we predict with it unseen extreme events? So can it really produce unseen extreme events? If it does, do the return period match the physical model ones, and is the dynamics similar? And so to validate this, we need an extremely long simulation. So that's why, for people in climate science, we have worked with plasm, such that we would be able to have an extremely long simulation. And so we have run our physical model for 90,000 years. So we got a 90,000 year simulation of a plasm climate model. And so then we took 100 years of data. Using this 100 years of data, we train a stable AI climate emulator with our architecture. And then we run the emulator 90,000 years. And then we can just compare the statistics of these two things. So most of this work has been done by Alex Wickner and Amaury Lancelin. So Amaury is a PhD working with me, and Alex Wickner is a postdoc in the group of Pedram Hassanzadeh at Chicago University. So here we will test the statistics. And so this is a case where it works perfectly. It will not always be the case, as I will show afterwards. So what you see here is a return time plot. So here you have a return period, and here you have something which corresponds to the extreme event we are interested in. In that case, it is a yearly maximum daily precipitation over the Persian Gulf. So you see here, for instance, that every 100 years, you have this value for the yearly maximum daily precipitation in that area. So you can study the risk, you can study it's basically the inverse of the probability. So you have several curves. So the black one is the ground truth that comes from the climate model. And the two others are our two AI-based architecture, Pangu and SFNO. And as you can see, up to statistical error for the rarest one, it perfectly fits. To compare, this is a Jeff fit using 100 years of data. So Jeff fits gives you basically something completely wrong. And so this is the error estimated for the Jeff fit. So the Jeff fits gives you a good error bar. So everything, the reality is within its error bar, but you see that its error bar is huge. Okay, so in that case, it works perfectly well. So we have a wonderful tool. So I show you now another case where we have a mean bias. So overall it works, but with a bias. And so this is for the yearly maximum daily precipitation over Florida. And you see that the shape is the correct one. It is still much better than a JEV, but we have a mean bias. So if we translate this curve by just the mean bias, then it's okay. But we have this mean bias. And so here we think that this mean bias comes from missing physics in the emulator. So probably here we would need to add the soil moisture, which is absent so far in the emulator. Okay, so this is just to say that it can work or it cannot work. Well, it's an empirical matter just to test this.
So when you're training, you're not giving the entire state vector system.
So in that case, our emulators emulates the atmosphere-only component. No, and that in that case it's a subset just because, as you know, there are time-scale separation, and so we have to develop the technology to deal with that. But we are, so Amaury and Vadim and other postdocs are trying to add to make AMIP kinds of emulator with ocean sea surface temperature and also including the soil moisture and other fields that are important for.
Explain what you meant by to go back to the physical model. The errors on the two emulators.
So I mean, this one is perfect. This one has an error. So we can go empirically, just try to build confidence on to know when it works, when it doesn't work. But another thing is to go back to the physical model.
But that sounds like you're trying to change the ground truth because your emulator didn't emulate it.
No. I just want to recompute this curve without the emulator, with the physical model. But
The small bias that you showed before. So when you were saying like this small bias about 0.5 Kelvin, and they propagate in the extremes, because also the physical models have bias.
exactly.
So which means that maybe explain why even with similar situation, they have a very small bias.
Yeah. But here it's we are in a perfect model setup, so we just compare the model with the emulator. Okay, it's not the bias with respect to the real world, which is discussed.
But I find it interesting also to see how small bias.
Yeah,
even similar model.
it's a much smaller bias than the one you have for the model compared to the reality. That's it. Okay, so the conclusion for this part is that the AI emulators trained on 100 years of GCM simulation produce very rare unseen events. The dynamics do agree with the physics-based dynamics. I have not shown you it, but we have checked that the evolution was through the same field. And the return periods are consistent, but are sometimes affected by mean biases. Okay, so in order to go back to the physical model, this is where we will use rare event simulation. We'll try to build this return time plot directly from the physical model. And so here the point is that it will produce physical model trajectory for extremely rare unseen events and estimate precisely their probability. So I will show you application first for long-lasting summer heat wave. So this is the 2-meter temperature, average over a large area. It's in Scandinavia, Europe, France, Alberta, Russia, and average over time. T here, the time window for the averaging could be 1 week, a few weeks, a month, or a season. Okay. So we have the question here is and was how to simulate a 10,000 year heat waves or sample or get 100 sample of a 100 year heat wave with a computation that costs only 200 years. Okay, so then that's where we use rare event simulation. So rare event simulation is something which date back to von Neumann, which first implemented by Kahn and Harris in 1953, and has been developed a lot in statistical mechanics, applied mathematics, and in my group we work on that for now 10 years, as I described in the introduction. Okay, so the first application of this to genuine climate model was done by Francesco when Francesco was a postdoc with me, and so you see I will explain you this very briefly. So the idea is that this is a sketch. This is not related to this paper. This is just a sketch. So you have time. So you have trajectories. You stop. You make selection. So here the green one has been selected. It has been duplicated. The blue one has been cancelled. So a new blue one has been built on the green one just by using the same initial condition plus a small error. And so then you do this selection, pruning, and duplicating from time to time, such that you get a biased ensembles of trajectory. And it is biased in a way that it will correspond to your extreme event. So it is biased in a way that you control. And so for this specific algorithm, we were using an example of a diffusion Monte Carlo rare event algorithm that was tuned by Giardina, Kurchan, Tailleur, Lecomte in order to compute large deviation for long time average. So I thought that it might be useful for this long-lasting heat waves. And so here is the formula where you see the formal notation for the probability for path for the initial model. It is tilted by an exponential factor where we tilt it here by an exponential of what we want to study, the time average of the spatial average of the 2-meter temperature. K is the strength of the tilting. This is just a normalization constant, such that this will be also a PDF, and so this will be the PDF that the algorithm will give us. So basically, we tilt in the path space, but we have this formula that tells us exactly how we tilted, and then we can, it's called importance sampling, we can go from what we compute to the reality by inverting this formula. And so we have done that with Francesco in 2018 in this PNAS paper, and then in another paper for the CSM model, which is one of the US model which is used for the CMIP experiment. So more recently, we have decided to do it for this case here somehow. And so we did that with Clément Lepriol, with Joy Montero, a colleague from India. And you can see here another aspect of this relevant simulation, which is the fact that it reproduces well the patterns. And so here we were studying heat waves over southwest India and Pakistan. So what you show here is the 500 geopotential height, 500 hectopascal geopotential height anomaly. So when it is red, you have an anticyclone and it is very hot. But this map is a map which is conditioned on having a very hot event here during a long time. And you see that condition on that, it is cold and anticyclonic here. It is hot and, it is cold and cyclonic here. It is hot and anticyclonic there, and so on. So you get a pattern at the hemispheric scale. And so with Francesco, we call this kind of pattern a teleconnection pattern for extreme. And so this pattern here has been computed with a very long 8,000 years control run. And this pattern has been computed using a simulation that lasted only 200 years. And you see that the two patterns coincide, meaning that we can actually compute correctly those patterns at a cost which is reasonable. Yes, Melinda? Oh, here we compare the two same things. So it's not written what it is, but it's probably something that like the last percentile for. They are the same event. They are defined the same way. The two things are the same, right? But this one, in order to get it from the data, you need 8,000 years. And with the relevant simulation, we can compute the same thing with only 200 years simulation. Okay, is it? Okay.
We should have, I saw that in the second picture, the connections, like the hemispheric connections are stronger. So I was wondering whether that heat wave is more rare, more extreme heat wave compared.
So there are many heat waves. So it's a, it's a composite map. So you say it is stronger. You mean this one is stronger than that one? Ah, yes. You have some discrepancy. You have some discrepancy. So whether this discrepancy are significant or not, I don't know. But overall, I mean,
It's very strong.
the average return time. So I think it's I don't, as I told Melinda, I don't remember. We should check that on the paper, but I guess it's about 100 years, something like that. But the real answer is that I don't know. I don't remember. I will check this after. Okay, so it works. It works, but the point is that it was working only for long-lasting event. When we try to use this algorithm or other algorithm, basically it was not working. And so the point here is that there is everything, the important thing is the selection rule you use there. And so we thought that it was not working because the selection rule we use was not adapted to other kinds of events. Here in this case, we study persistent event. So the selection rule is very simple. We just select trajectory based on the last value of the observable during a period of time, the increment of the last value. Okay, so but it's good enough for this phenomena, but it's not good enough for other phenomena that have a more complex dynamics. So what we have done is to couple the two things. So basically, we will use the same kind of algorithm, but here, when we have to select, rather than guessing, we will compute the probabilities to get the event using the emulator. So because we are able to run now the emulator very easily and it doesn't cost much, for each of these trajectory locally, we can estimate the probability that it will lead to the event. And then we make a rule, a selection rule, that is really informed by the actual probability of the future event. And so this is what we call coupling dynamical emulators with relevance simulation. And it's a paper that has been just published a few weeks ago in a physical review letter. And so you can see here the case of 7-day extreme heat waves over France. We were not able to get this working before. So now it works. You can compare the control run in black and the emulator coupled with the relevance simulation in blue. And so you see that there is a perfect agreement, even for events that are very rare. And so here, for the black curves, we needed 50,000 years. And for this one, we need only 400 years. Okay, so coupling the two approach, we are able to get the relevance simulation working. So then we can, that's what I meant when I say we will go back to the physical model. We can go back, so we will not trust the emulator. We'll just use it to give us an indication of the reality. And we will go back to the physical model to actually estimate the real probability. Okay, so this is a paper that it has been actually featured by Nature at the time of the submission to arXiv. And it has not been published in Nature, it has been published in a PRL a few weeks ago. So I still have 5 more minutes to show you a few examples of application. So I will show you probably just one of them. So currently we work on 3 different projects. So we have, so I lead with Laurent Dubu from RTE in France, a framework program which aim is to understand the effect of rare climate events on the electrical system. And so RTE is the French company that work for the French state in order to manage the electrical system at the national scale, and also to make the prospective studies for the future of climate change. So they are really the most competent in France and maybe also across Europe in order to study the impact of climate event over the electrical system. So climate events are very important because in the future, most of the electricity will be produced by renewable energy, so wind, solar, and the demand itself depends much on temperature. So all of this depends much on the climate. And so here we have we are a group of about 10 people on at IPSL, and about 5 to 10 people within RTE, and we coordinate some research to do that. So another example is this Southern Asia heat wave study. And so here we have a project which is funded by the Belmont Forum, for which we work with Indian institutions in order to do the research which is useful for them. And so it is also a project which is with some American colleagues. And the final one is for a few years, I set up a project to study drought as a systemic driver of climate change in France. So this is Leah Rosenberg that will start a PhD to work on that. So all these 3 projects, they are transdisciplinary. And so this is very important to me. What does mean transdisciplinary? It means that it is interdisciplinary. So we have math, physics, climate sciences, and whatever needed, social sciences, economy, and so on. But it's not just academics, it is also the stakeholder. So we built the research project from scratch with the stakeholder. So we don't decide which are the important questions ourselves in the academics, but we built the question with them. So I will just show you in 2 minutes one thing, which is the third tool we use, which is the Bayesian general extreme value theory. So here the point is to go back to the actual observation in the real world using the model output. Okay, so for instance, a question asked by RTE, they built a new power line here in this part of France. So it's a big deal, 100 kilovolt and 7.6 gigawatt. And they want it to work for the next century. And so for this, they need to know the extremal possible temperature at that point in France for the next 100 years. And so this is the question: what is the maximal possible temperature over continental France? So in order to do that, we have used a method that was developed by Aurélien Ribes and Johan Robin. And this work has been done by Peter Werner. Peter is here, postdoc working with in this research framework with RTE, with myself, Laurent Dubu, and Johan Robin. So here the point is that we'll use GEV, General Extreme Value Theory. We will fit the General Extreme Value Theory parameters on a set of climate model output. This will give us a prior distribution for these. And then using the actual observation data, we use a Bayesian approach to estimate the value for the GEV parameter. So then unlike before, we have lots of statistics because the model output we have lots of models, and each model can be run a lot of time. And so then we can estimate faithfully JEV parameter. But because the model have some biases, we use a Bayesian approach to go back in the real world. And so you see here, for instance, our estimation of upper bound, median, and quartile in future climate for the temperature at this power station. So you see this is the median, this is the two quartile, upper and lower quartile, and this is the upper bound for this distribution, which is bounded. So this is the maximum possible temperature. And so all these dots are actually the observation point. And as you can check, I mean, about half of them are below the median, and a quarter of them is. So it fits with the data, and it also fits with the model output that inform us about future climate. So this is with a scenario. Okay, so I guess I slightly went off my time, so I will stop here. I have not talked about tipping point, but basically the idea for tipping point is that it's the same problem, it's the same lack of data issue. If we want to study tipping point with climate models, we don't have observation data. It is very difficult to run the models very long if we want to use a comprehensive model. And so we need to, so I just show you one slide, which is to show you that Francesco has made interesting work on that, applying Plasim model for studying the AMOC tipping point. And then I just tell you that we are trying to develop the same tool for tipping points. Okay, so thank you for your attention.
Yeah, we actually had a lot of questions already during the. If there are more questions, maybe I have, but this is priority. Yeah.
I have one. If I understand correctly, the emulators for Plasim, they're pre-industrial runs, right? There's no climate change. And do you have an intuition of how you can use these tools when you actually have something that changes?
Yeah, with Plasim, we were trying to develop the methodology. So we were using a very long control simulation that lasted. They are not pre-industrial. It is the climate of the 2010, this one. But now we are learning an emulator for the IPSL model. And the simulator should work with also with a scenario for future climate. It's a technical matter. I mean, when we have to work in a non-stationary setup to have another variable that tune the CO2 of the average global warming level, something like that. So yes, we will do that soon.
Any questions? Yes.
I was surprised that the emulators are so stable, considering that it's we are talking about the climate, right? And the emulators don't learn conservation laws. And I remember sort of work of Gabriele Messori showing that AI for climate models, like it drifts towards a non-physical.
Yes.
So do you have a trick, or what do you do?
So we have empirical tricks, and it is a huge work. I mean, it was a huge work by Amaury and Alex to get the simulator stable and have good statistics. So they have to tune a lot of things. So the trick is just good cooking so far. Okay, so but it works. Okay, so but it's also the case for the emulator for the weather. Right? There are lots of choices which are at this stage arbitrary, and people just go empirical. Okay, so then you can ask. There is a question that I ask to many mathematicians, including several present here this week is if you are which kinds of mathematician should be able to understand comment dire, numerical analysis, this AI-based approach, the technical aspects of it, such that there is a proper mathematical framework that will ensure from scratch the fact that it will be stable and that it will correctly produce the invariant measure. So that we can go from empirical to something more, you know, sure. I mean, from the point of view of what we actually do. But I don't know which kinds of mathematician can answer this question so far.
An AI mathematician.
Matthew Colebrook is running the other program.
What is the
Matthew
AI?
Colebrook is running the other program at the Institute right now.
So your program, Matthew?
Yeah, Gary is a coordinator.
Gary is also, well, maybe. Sorry? It's a hard problem, yes. It's certainly a hard problem. So do you think I should discuss with Matthew? Yeah, I will definitely talk to him.
The fact is, though, that the way you're using it for the importance sampling, it doesn't matter whether having a good emulator speeds you up, but it doesn't. If you have a bad emulator, it only slows you down. It doesn't make the final outcome less reliable. Is that not correct?
Well, this is correct in principle, but this is correct in the limit when you have numbers of clones in your algorithm, which will be infinite. In practice, because it is very costly and we can use only 100 or few hundreds of clones, if you want it to actually correctly work, you need to be as good.
An error that you're unaware of.
An error about what?
You won't get an error that you're unaware of. Whereas if you were just using the emulator
That's right.
on its own to predict these rare events, you wouldn't know whether the result was dependable.
Exactly.
But the way you're using it means that when you do get a result, it is dependable.
Exactly. You can test whether your relevant algorithm converge or not. You can do things. Yes.
I have a question myself, if I can. It's a bit a negative one. It's one that I ask myself a lot when we work on this thing. I think we talked about it a bit.
Good.
So the point is that the physical climate model that eventually you go back to for your event sampling, they are calibrated on the bulk of the statistics. That is what you have from data. So, and then we use this method to go to a return time of 10,000, 100,000, 1 million years. Can we trust the models in the tail of the distribution? And if we don't, is it still very legitimate to use this tool?
So of course I don't know the answer, but some indication. Here you see that the emulator learned the dynamics using 100 years of data. So he learned the bulk dynamics. He learned from the bulk dynamics, and it works. So it means that it is the bulk dynamics that produce this extreme event. It's just the bulk dynamics in a rare setup. Okay, so of course it will not be always the case. You can have rare events that are produced by something else that you have not learned. So
No, I simply imagine the scenario in which we have computed this return time of 100,000 years using a numerical climate model that was calibrated in a certain way, and we don't know exactly how that works, if the representation of reality is good in the tail, and then we go to tell these numbers saying, oh, this is what really happens in the real world. And I'm a little, sometimes uneasy about that.
Well, the only thing that we can say is that this is the best method we have so far, or not.
Yeah, last question.
Thank you so much.
Currently, we use the 100 years data to predict futures. And I want to ask if this is a forward process, what if we use the backward process to use this data to better to simulate the history data? So that
Sorry, I didn't get. If it
I
is
mean,
which
here
process?
we predict for the future.
Yes.
For like 10,000 years. What about use this framework to put it into better to fit the history data to see how it's the backward of the previously ancient history.
You mean to study Asian climate, extreme events? Yes, I guess if we use a climate model which is suited for Asian climate, it would work. Did I understand you well?
Saying, could you predict the past? In other words, if you have your 100 years data and you're in some kind of stationary state, you should equally be able to predict historical or get the statistics of historical rare events rather than future ones, for which you may have data that you could use. But I think if you take your 100 years from the beginning, the early part of the 92,000, it doesn't make much difference.
And here we have this data we predict. What about here we have this data to see how the ancient data should go, because it's also like after this. What we predict is for the forward part, and this one for the backward part with the same framework.
So the 100 years we use is anywhere in the 90,000 years. So from this point of view, there is no future or past. It's anywhere.
This is not a calibration on historical data. This is a calibration on stationary run, so there is no future or past or anything like that. So
Maybe your question will be, I'm not sure I understood it, but maybe we should discuss it later, because in the future we will do the same thing using scenarios where there will be historical part, current climate and future climate. So it might be relevant if I can understand it.
yeah, maybe we take a break now because then there's talk of Susmita, so we come back in